To explore this question, I will mainly discuss about research background, methodology, experiments, and possible future works in this presentation. To start with, why we focus on fluid dynamics? It is regarded as one of the most important factors of engineering design, for its wide applications and wide coverage of people under influence. Basically, on a large scale, such as designing a spaceship, into a smaller scale, such as biological injection into blood vessels, are all applications of the study. They all need to minimize their resistances with the study of fluid dynamics. And also for this reason, there are huge civil application potentials. So generally, everyone who drives a car, flies on a plane, or simply lives in a building with AC or turbines is under its influence. But the two key problems of the current designing process lay in its theory and application. The knowledge barrier is set by Navier-Stokes equation itself, which is the governing equation of fluid dynamics. It has its properties of complexity and insolvability. Because of its chaotic nature, even the understanding of the equation is challenging. In fact, it still remains one of the 6 hardest unsolved mathematical problems in the world, being awarded for $1 million for a proof. Also, it has no closed-form solutions due to its chaotic nature. Therefore, for engineers to design, experts are involved in the process to first guess on the possible shapes and then prototype the results. Such process needs a lot of human domain knowledge and sets a natural barrier. The result produced by such estimation later moves on to be physically prototyped and tested, usually in a wind tunnel test. Such tests for physical property is a waste of both time, space, and resources. There are few previous works related to remedy the mentioned problems. Firstly, computer simulation. Now engineers can design based on simulation results from platforms such as MATLAB. However, the expert input is still unavailable and there is no way to make sure that the shape is actually optimized. Bayesian optimization done at Stanford University is the only study I found that is similar to our attempt to apply machine learning. However, their methods need too much data to train and still require some human domain knowledge to eliminate possible mistakes in prediction. Therefore, there are two key questions for our study to deal with. How can we make this design process even less computationally expensive with less human domain knowledge? Our solution is DNN over active learning. Now, let's look into methodology.